Hello everyone, welcome to EGN 3343 Thermodynamics, and today we are going to talk about the conservation of energy principle for closed systems, which is going to lead to the first law of thermodynamics. So essentially, we are going to focus our attention for the first few weeks of the semester to the study of thermodynamic processes occurring in closed systems. Okay? Remember that last class when we defined what a system is, we classify them in two main forms or two main classes. Closed systems, or control masses, is a system that can actually change shape or size and size during a process, but mass cannot escape or enter through the boundaries. It cannot enter the system or escape the system. The open systems, on the other hand, are also called control volumes because their volume is fixed. They cannot change shape or size during a process. However, mass is allowed to cross the boundaries of the system and is allowed to enter and leave the system. So we are going to, as I said, we are going to be concentrating on processes occurring on closed systems, and we are going to be formulating and enunciating the conservation of energy principle for these type of systems. So let's consider a closed system. It's a system that sometimes, and more often than not, will be depicted or illustrated by a piston cylinder assembly. We have a piston inside a cylinder, and the system is actually the gas inside the piston cylinder assembly. And at state number one, which is in equilibrium, we have certain properties as we defined them last time. We have pressure, we have temperature, we have volume, and we have another property that we haven't defined yet, which is energy, or total energy, E. Notice that it's a capital letter, so therefore it will be an extensive property, therefore it will have a corresponding specific property if we divide by the mass of the system. Again, this is a closed system. That means that the mass of the system cannot escape the boundaries. That piston is allowed to move during the process up or down, which means that the system is going to change shape or size, but the mass is always tracked throughout the course of the process. So we have a state one. We conduct some processes, and maybe add heat, or apply work, or remove heat, or let the system perform some work, whichever form of work or heat interaction we have, and then we end up with a second state on the same system. And let's assume that this is an expansion process. It's a process by which the volume 2 is larger than the volume 1, and as expected, the rest of the quantities might be different. Okay? At least two of these quantities are going to differ from the quantities in state 1, because if the volume changes, in order for the system to maintain thermodynamic equilibrium, at least another property has to change. You cannot maintain all but one of the properties constant. So we start with P1, T1, V1, and E1, and we end up with P2, T2, V2, and E2 in general. But it might be that just two of these properties changed in particular. So what do? We are going to conduct a balance of energy. And the principle of balance of energy states that energy cannot be created or destroyed. It can only be transformed. That is, well, in thermodynamics, we only work with two forms of energy. We work with thermal energy and we work with mechanical energy. We either input or output thermal energy in the form of heat to conduct this process, or we input or output mechanical energy in the form of work, and these properties change. Now, the principle of conservation of energy says, again, that the energy cannot be created or destroyed. So this property that we haven't defined yet, called energy, the total stored energy of the system, which is a combination of many energies, can be affected by adding heat or adding work, or both, adding heat and work. So that's the balance that we are going to perform. So we are going to perform an energy balance on the system between state 1 and state 2. That is, the energy of state 1 can be affected by adding heat or removing heat from the system, by performing work on the system, or by performing work by the system. Okay, notice that heat into the system is positive, heat out of the system is negative. Work done on the system appears as adding energy to the system, and work done by the system appears as adding energy to the system. That all balances out to give you what the energy state or the energy value state 2 will be, E2. So again, we start with a value of contained energy. Notice that E is referred to the state because that is a property of a state. Remember, definition of a property. A property, as long as you can assign a value of a property to a particular state without knowledge of the history of the system, that qualifies to be a property. So the energy content, E, is in fact a property. Now we're adding things that are not properties. They are transient forms of energy. They're all units of energy because we're adding and subtracting. So we take an energy, we add thermal energy, we add mechanical energy, we subtract thermal energy, we subtract mechanical energy, and we end up with, after this balance, with energy 2. Okay? So let's perform an energy balance on the system between state 1 and state 2. We end up with these particular form, and E, as I said, represents the stored energy of the system, the total stored energy of the system, which, as I said, is a combination of different energies. Now consider a closed system again, and we're performing the same energy balance. E represents the total stored energy of the system, and Q and W represent transient energies which cross the boundaries of the system as heat and work, respectively. We already talked about heat and work and what they do. Notice that I'm saying that they cross the boundaries of the system, and we're talking about a closed system. We said in a closed system, mass is not allowed to cross the boundaries. Mass cannot enter or escape the system. But we're not talking about mass. We're talking about energy in the form of heat or mechanical energy, W, or mechanical energy in the form of work. Okay, which work can actually be other types of energy. It can be not only mechanical, it can be chemical and so on. But we are going to limit this, confine the work in thermodynamic processes to mechanical work. Okay, so we have a form of stored energy, which qualifies as a property, and then we have forms of transient energies, energies that cannot be associated with a state. Q and W cannot be associated with a state. We perform Q throughout a process. We perform W throughout a process. We cannot say the Q at state 1 is so much and the Q at state 2 is so much. We cannot say W at state 1 is so much and W at state 2 is so much. That doesn't exist. Now we are going to rearrange this equation to put all the transient energies on one side and all the stored energies on the other side. That means we're going to take the E1 to the right hand side and we're going to keep all the Q's and W's on the left hand side. And we are going to group the Q's together, Q in minus Q out, and we're going to group all the W's together, W on minus W by. And what we're going to end up with after rearranging is basically Q in minus Q out. This is the same equation. All we're doing is rearranging. Minus W by minus W on. Notice W by was negative and W on was positive, and that's why I put in this minus sign at the beginning of that parenthesis, equals to the change in energy of the system. So we can establish that the change of energy of the system, energy of state 2 minus energy of state 1, the increase or decrease of energy or stored energy of the system can be affected by either heat or work. And by doing so, what we are doing is actually setting up a standard for the sign of the Q and for the sign of the W, the sign of the heat transfer and the sign of the work. It's a convention that we're establishing in this class. What positive Q means, into the system. If the system is receiving heat from the outside, then that is positive Q. If the system is releasing energy in the form of heat to the outside, to the surroundings, that is called negative Q. If the boundaries are insulated, the system is adiabatic, Q cannot cross the boundaries, and then Q is equal to 0. On the other hand, work means if the system performs work, mechanical work, that is going to actually lead to expansion. If the system expands, work is positive, done work by the system is positive, and done work on the system is negative. So if the system expands, work is positive, and the system contracts, work is negative. In terms of mechanical work, and we're going to get to that point in a second. So again, we are going to rename now Q net, using this convention, the convention of signs for heat and work. Q net is equal to Q in minus Q out, which defines positive Q going into the system. Q in is positive, Q out is negative. On the other hand, we're going to define the net amount of work as W by minus W on. If the system performs the work, it's done by the system, then we assume that that work is positive. Work done by, meaning expansion, is positive. Work done on the system, meaning contraction, work is negative. If the system doesn't move in volume, if the system doesn't change size, then the work is equal to 0. This only applies, this particular concept here only applies to closed systems. And remember, we are only considering closed systems in this balance, in this formulation. So at the end of the day, when we plug in these definitions of Q net and W net, remember, these definitions not only define what the net amount of heat transfer and the net amount of work is, but they also define the sign. It basically leads to the first law of thermodynamics. Basically leads to a balance of energy that can be construed as the first law of thermodynamics. It says that the change in energy in a system from initial state to final state, and this delta means change. It means E final minus E initial. It means E2 minus E1. The change of energy between two states, whether the process is quasi-static or non-quasi-static, whether the process occurred fast or slow, it's going to happen only due to a net amount of Q and a net amount of W, a net amount of heat transfer and or a net amount of work. And that under the convention that Q is positive in the system and W is positive done by the system expansion. Okay, so this is the final form of the conservation of energy equation for closed systems. Later on, we're going to define what this Q is. We're going to define in detail what this W is, and we're going to define in detail what this E is, and then we're going to just basically, given different names, we're going to rename this formula or this conservation equation to or as the first law of thermodynamics. Okay, so we have formulated the conservation of energy principle. Energy in a system can change by either applying heat or applying work, or both. Now, we've defined energy before. It's the ability to do work, overcome a resistance, or cause an effect. This is the basic definition of energy. Now, in our balance of energy equation, which will later become the first law of thermodynamics, we have many forms of this energy. We have one called Q, we have another one called W, and we have another one called E. And there are distinctive differences between these. Now, we have categories of energies. Energy can either be stored, meaning contained or stored in the mass of the system. That will be E. The total energy of the system is the total stored energy of the system. We can define it as a property. We can calculate, measure the amount of energy contained within a system in terms of kinetic energy, whether if it's moving, potential energy, if it's elevated or being affected by a field force, internal energy, molecular energy, magnetization energy, strain energy, surface energy. Those are quantities of energy that can be stored and associated with the state of a thermodynamic system. So they qualify as properties. The other forms of energy, which have the same exact units because they are a form of energy, ultimately, are the transient form of energy. The transient forms of energy, they cross the system boundary. They're not associated with mass crossing the boundary. Remember, we're talking about closed system, so mass cannot cross the boundary. It's just energy in the form of heat or energy in the form of mechanical energy work. Now, these transient energies cannot be associated to a state. Again, I've repeated these about 10 times already. Transient energies, heat and work, cannot be associated with a state. They are associated with a process. Okay? Q occurs during or throughout a process. W occurs during or throughout a process. We cannot say that the work at state 1 is so much and the work at state 2 is so much. That doesn't exist. Now, the nature of E, the total stored energy, is given by many different forms of energy that can be associated or related to the state of a system, because it's stored energy, after all, is a property of this thermodynamic state. The first one and most important one from the thermodynamic point of view is the molecular or internal energy. Internal energy, and it's denoted by capital U when it's extensive and lowercase u when it's intensive. So energy U is one particular component of the total energy of a system that defines the state of a system that is related to the molecular configuration of the gas or liquid that compose the thermodynamic system. Okay? It has to do with microstructure. It has to do with the internal composition and the internal motion of those molecules that cannot be seen macroscopically, cannot be seen in bulk. That is the most important form of energy from the thermodynamics point of view. The other ones are very common. Motion. If the system is actually moving internally, if the gas or the liquid is actually moving in bulk, not microscopically. Microscopically, a system or a gas or a liquid is always moving. But as a bulk, let's say that the gas is moving around the system inside the piston cylinder assembly, that's kinetic energy. We also have position or potential energy. PE, potential energy. It can be due to gravitational forces, electrical forces, magnetic forces, anything that comes from a potential, gravitational potential, electrical potential, magnetic potential, leads to a potential energy. Okay? Surface energy, strain energy, flow energy, and many more. So ultimately, the total stored energy of a system at a state 1 or 2 or initial or final or intermediate, whatever it is a summation of all these forms of energy. U, the internal, kinetic energy KE, potential energy PE, plus all the other forms of energy. Now, in the study of thermodynamics, we are commonly going to neglect some of these energies because they really do not change that much. Remember that the first law, that the conservation of energy doesn't show E directly, it shows a change in E on the right hand side. How much E changes from state 1 to state 2. And how much E changes? Well, that means how much the internal energy changes, how much the kinetic energy changes, how much the potential energy changes. So think of potential energy, for example, which has to do with elevation of the center of mass of the system. We know that the system weighs something, and we know that there's a gravitational pull on that weight, or on that mass. If we have a system inside a piston cylinder assembly, and then the piston is at this location, we have the center of mass right in the middle, and that center of mass is at an elevation with respect to a reference. Okay? If the system compresses or contracts, that center of mass lowers. So the actual potential energy value at state number 2 is lower than the potential energy value at state number 1. That means that the potential energy has changed. But the way it would change, it would be negligible compared to the way the internal energy U will change. So the changes in kinetic energy and potential energy and any other forms of energy are always going to be, in the case of closed systems, negligible when compared to the changes of molecular configuration or internal energy U. Okay, so that is a stored energy, E, the one that's on the right hand side of the balance of energy. Let's talk about now the transient energies, the Q and the W. Transient energy is energy crossing a system boundary not associated with mass crossing the boundary. Remember that mass cannot cross the boundary, obviously. This is a closed system. These energies actually cross the system by whatever means. Thermal energy, either by radiation, convection, conduction, mechanical energy by expansion and contraction of the system. Transient means that it cannot be associated to a state. It cannot be associated to a state. Therefore, these forms of energy are not properties. These forms of energy are processes. They exist only during the transfer process. We consider two forms of transient energy, heat and or work. We already know that. Q for heat, W for work. We call transient energies processes, either a heat process, a work process, or a heat and work process. Those are the three types of thermodynamic processes that we are going to be looking at in our analysis of thermodynamics. Now let's start with heat, Q. Heat is energy transfer due to a temperature difference between the system and the surroundings. Okay? Now, we have to be careful with the definition of heat. Remember that heat is not a property. Heat is not associated with a state. Heat is associated with a process. Heat is transferred from state 1 to state 2 or throughout the process that occurs between state 1 and state 2. Okay? Now, heat doesn't occur internally. It occurs from outside to inside or from inside to outside through the boundaries of the system. If the surroundings are hotter than or a higher temperature than the system, then there's going to be heat into the system. The heat always travels from high temperature to low temperatures. If the system is at a higher temperature than the surroundings, then there's going to be a heat transfer line or arrow pointing to the outside. That is only possible when the boundaries of the systems allow for the transfer of heat, when they're not isolated. If the boundaries are thermally isolated, it really doesn't matter if the outside and the inside are at different temperatures. The transfer of energy in the form of heat is not going to occur. Now, again, when defining heat, you always have to be aware of the fact that heat is not temperature. And I am going to repeat this throughout the semester many times. I'm going to stress this concept. Heat is not temperature. Okay? The fact that you add heat to a system doesn't mean that you are going to be raising the temperature. More than likely the temperature is going to go up, but there might be cases where the temperature stays flat and you're still adding heat. Okay? So one doesn't necessarily lead to another. You can conceive a thermodynamic process in which you add heat and the temperature of the system actually goes down by actually controlling the rest of the properties, the volume, the pressure, and so on and so forth. Okay? So heat is not temperature. Obviously it's not, because heat is a transient form of energy. Temperature is a property. Temperature is not even an energy anyways. Now, details of determining the amounts and or rates of heat transfer are beyond the scope of thermodynamics. In thermodynamics, we don't calculate the amount of heat using external mechanisms, like we don't apply conduction processes, we don't apply convection processes, we don't apply radiation processes, or the combination of these. Heat is either a given, or heat is something that we can find directly out of the first law of thermo. Okay? So heat is not something that we can calculate through a constitutive relationship. At least in this class, you have to take a heat transfer class to be able to calculate the heat. Heat will be either the unknown, which may be determined from knowledge of other terms in the problem. It will be the unknown, but the only way you can determine it, since we are not going to look at the mechanisms of heat transfer, the only way you can determine it in thermodynamics is through the first law of thermo, through the balance of energy, which is Q minus W equals the change in energy. If you know the change in energy and you know the work, then you can calculate Q. That's the only way. It also can be zero in an adiabatic process. Adiabatic process means that there's no heat transfer. Either the system is in thermal equilibrium with the surroundings, or the system and the surroundings are actually separated by an insulated boundary. So the heat can be neglected in adiabatic processes, or it can be given. The value of heat can be given, and then you perform the problems in the balance of energy to determine other things from the first law of thermodynamics. Okay, now that is the first form of transient energy, heat. The other form is work. What do we do with work? Work is energy transfer due to a potential difference other than temperature. It's a potential difference other than temperature. That means it has an operational definition. Work is an interaction between a system and its surrounding, and is done by a system if the sole effect external to the system could have been the raising of a weight. Okay? Work is mechanically defined as raising of a weight through a distance. It's force times distance. That's what work is. And it has units of energy. Force times the distance. So if we raise a weight over a distance d, multiply the two, we get work. Obviously, that can be translated into other parameters. It can be translated into quantities that are associated with the thermodynamic process or thermodynamic state. So, work can be either of the form of expansion and compression of the system. That is the mechanical work. That is the work that we are going to take into consideration in this class. That is the work that we are going to be calculating. And as opposed to heat, we can actually calculate work. We can calculate work by some expressions and some formulations if we know how much the system is expanding or contracting throughout the process. And we know how is this contraction or expansion occurring, at what rate and in what shape, then we will be able to calculate the mechanical work. There are other forms of work. Work of a reversible chemical cell, so chemical work. Work in stretching a liquid surface. Work done on elastic solids. And work of polarization and magnetization. These works are always going to be, in the majority of our cases, unless otherwise stated, will be negligible. The only work that we are going to be considering in thermodynamics analysis is the expansion and compression work, which is the mechanical work. And remember, if a system expands, the work is positive. If a system compresses or contracts, the work is negative. That means that if a system stays the same size, there's no work. So that these definitions and these statements lead to the form, the standard form and the formulation of the first law of thermodynamics. Remember that we started everything by performing a balance of energy. The common statement of the first law of thermodynamics, which is expressed in this equation, which I've already determined, means that the change in energy of a system can be accomplished by either heat or work or both. But the statement, the original statement, formal statement of the first law of thermodynamics reads, when a closed system is altered adiabatically, the work is the same for all possible paths which connect two given equilibrium end states. Now, what does this mean? It actually doesn't read too much what we see on this equation. This is the equation of the first law of thermo, and this apparently reads something completely different. Now, let's look into this. When a closed system is altered adiabatically, that means Q is equal to 0. Let's eliminate this Q from the equation. All we're left with is work and delta E. Okay? That means that the work is the same. The statement reads, the work is the same for all possible paths which connect two given equilibrium end states. What are the equilibrium end states? State number 1 and state number 2. In state number 1, you have energy 1, E1. In state number 2, you have energy 2, E2. Okay? Regardless of how we go from E1 to E2, if we go in a curve like this, or if we go in a curve like this, if we go rapidly or slowly, or if we go convexly or concavely or in a straight line, if the process occurs adiabatically, Q equals 0, the work will be the same to get you from one end to another end, regardless of the path throughout. This is kind of a consequence that you can read from this equation. Another common statement of the first law of thermodynamics, and actually simpler, is the change in the stored energy of a closed system equals the sum of the net heat transfer and net work interactions on the system. There you go. The change in total stored energy of the system in a closed system is either due to heat or work. This is a statement that is read directly out of the equation, out of the formula. Now, the first law of thermodynamics, if we express it in words, states delta E is equal to Q minus W. If we apply Q, we change energy. If we apply work, we change energy. Remember that Q into the system is positive, out of the system is negative. Work, expansion is positive, contraction is negative. That's all you have to remember. The change in the amount of energy contained within the system during some time interval equals the net amount of energy transfer in across system boundary by heat transfer during the time interval minus the net amount of energy transferred out across the system boundary by work during the time interval. So Q in is positive, W out or W expansion by is positive. You can also express the first law of thermodynamics in rate form. Rate form meaning, well, divide everything by time. And let's just look at, instead of energy, let's look at power. Remember that when you divide energy over time, you get power. The fundamental unit of energy in the SI unit system is the joule. If you divide a joule over a second, that's energy occurring in a space of time, then what you have is power, watts. 1 watt is equal to 1 joule divided by 1 second. So in rate form, the time rate of change of the energy contained within the system at time t equals the net rate at which energy is being transferred in by heat transfer at time t minus the net rate at which energy is being transferred out by work. Mechanical power, thermal power, they both affect the rate at which the energy of the system actually changes. And the equation for that comes like this. So the change of energy with respect to time, that's what the EDT is, the change of energy. Don't worry about these differentials. It's just an expression. The change of energy as a function of time, that's the time rate of change of energy, equals Q dot minus W dot. Q dot being the rate at which energy is being transferred in the form of heat, and W dot means the rate at which energy in the mechanical energy is being transferred in the form of work, that is power. Okay, so this is the first law of thermodynamics. These are the expressions, these are the variations of the first law of thermodynamics, and we are going to get to apply this principle of the first law of thermodynamics over and over and over the next few weeks. Okay, and that's going to lead to the solution of many problems, at least for closed systems. Now let's make a parenthesis here, and I'm going to just show you 3 slides of the energy analysis of cycles. Okay, we have stated that this is the first law of thermal. Change of energy is equal to Q minus W. Change of energy of a system that occurs during a process of heat or work or both. Now, what happens if you have a set of processes that lead to the initial condition? If you have a set of processes that go from 1 to 2, and then from 2 to 3, and then from 3 to 4, and then from 4 back to 1. It doesn't necessarily have to be 4 processes. It can be 5, or it can be 2 or 3. 2 or more is fine. We can conceive a system that undergoes transformations through thermodynamic processes, starting at state number 1, going to state number 2, and then from state 2 to state 3, and then from state 3 back to state 1. That is called a cycle. If you close, you return to the initial condition, it is called a cycle. Now, what happens in a cycle? If you return to the initial condition, all the properties of the state are going to be the same. The initial condition states that basically all the properties, P1, V1, T1, and energy 1 are in harmony, they're in equilibrium, and as soon as you return to that state, all these conditions are the same. All these properties are the same. So, essentially, a thermodynamic cycle is a sequence of processes which periodically return the system to its initial condition, to its initial state. 1, 2, 3, 4, and 1, or 1, 2, 3, 1. Okay? It can be a combination of 3 processes, 4 processes, 2 processes, as long as you return to the first one. Now, if you take a look at the first law of thermodynamics, which applies, obviously, it applies for one process and applies to the next process, it applies to the next process. Okay? The change in energy in a process, work and heat. The change in energy in the next process, work and heat. From 1 to 2, from 2 to 3, from 3 to 4, so on and so forth. If you add them all together, what's going to happen is that all the energies are on the right-hand side or on the left-hand side are going to cancel, the E's. Because delta E states E2 minus E1 in process number 1, plus E3 minus E2 in process number 2, plus E4 minus E3 in process number 3, plus E1 minus E4 if you're returning to the initial state in process number 4. All these energies E's are going to cancel with each other, and you're going to end up with the right-hand side equals 0. So what happens is that since delta E in a cycle, as long as you return back to the original point, delta E is equal to 0, the first law of thermal for the entire cycle reduces to the heat of the cycle, the heat transfer during the cycle, which is a combination of all the heats transferred on process number 1, process number 2, and all the different processes, equals the amount of work performed throughout all these processes. Work from 1 to 2, work from 2 to 3, so on and so forth. Now, this is the energy balance for a cycle. You just assume, obviously, energy, the stored energy doesn't change because you're returning to the initial state. So the amount of Q that you put in and out throughout these processes equals the amount of work that you do by and on the system. There are 2 types of cycles in thermodynamics. So we're going to get to study these cycles towards the end of the semester. Towards the end of the semester, we're going to study these cycles in a lot of detail. Once we establish all the formulations, the first law, second law of thermal, closed system, open systems, define entropy, and so on, we're in a position to analyze power cycles and refrigeration cycles. A power cycle is intended to produce a net work output from heat input. So somehow, you input heat to obtain mechanical work. You input heat rate to obtain mechanical power, like what you do in the engine of a car. You use the chemical bonds of the hydrocarbon and the fuel to burn, input energy in the form of heat into the air contained in the piston cylinder assembly, and by doing so, you create an explosion and create mechanical power. So you're transforming between thermal energy to mechanical energy. And that is a power cycle. You use heat to create work. So the amount of work in the power cycle is always going to be positive. The measure of performance for a power cycle is its thermal efficiency. Thermal efficiency, which is given by the sign eta, the thermodynamic efficiency of a cycle, is given by what you obtain divided by what you put in. That's a measure of efficiency in whatever you do. Productivity, efficiency, that's all the same. It's whatever you obtain out of the cycle or out of the process divided by whatever you put in to the process or put into the cycle. Okay, notice that we're not dividing W cycle over Q cycle because that will always give you 1. According to the conservation of energy in a cycle, W cycle is equal to Q cycle. We're breaking up the Q into whatever amount of Q is put in and whatever amount of Q is put out. Okay? Now, in a thermodynamic cycle such as the Otto cycle, which is the one that occurs in gasoline engines, you have an amount of Q that you invest, you put in, which is the explosion of the fuel in the air, and then you also have waste energy. That waste energy is Q out. There's no way of getting around it. You always have waste energy. So by definition, the thermodynamic efficiency of a cycle is 1 minus Q out divided by Q in. If you perform this analysis saying that W of the cycle is equal to the Q of the cycle, and you define the Q of the cycle as Q in minus Q out, the thermodynamic efficiency of a power cycle is 1 minus Q out over Q in. On the other hand, you can actually reverse a cycle. You can have a cycle for which you actually input work externally. You plug in a motor, an electric motor, or maybe a gas engine to input work into a system, compress the liquid or gases in the system in a way that you can use it to subtract heat from some surroundings, like this room, for example. So what you put into a refrigeration cycle is work, and what you obtain is heat. So the definition of efficiency is actually reversed for refrigeration cycles. A refrigeration cycle is intended to use work input to cause the transfer of heat from a low temperature to a high temperature. Okay? So basically, we use energy in the form of work. We input that energy in the form of work to a system, make it compress. We're going to get to the details of that. And we actually use some thermodynamic parameters of the system to subtract energy from a room, for example, in the case of an air conditioner. The measure of performance of a refrigeration cycle is given by the coefficient of performance. And in this case, it's called beta. It's no longer called eta, like in the case of power cycles. And as I mentioned, it is reversed. In a refrigeration cycle, what you put into the system is the W of the cycle. What you put in is work or power, mechanical work. And what you obtain is that Q in. What you obtain is the amount of Q that you put in to the system that you're subtracting from a room like this. You put into the system. And in that case, in the analysis of a thermodynamic cycle, the system is the refrigerant contained within the compressor and contained within the circuit of the refrigeration unit. Okay? This room is actually the surroundings. So that is a parenthesis that I made to talk about or to introduce the concept of cycles, because that's ultimately what we are going to do in this class. Ultimately, we're going to get to the analysis of cycles in detail, the different types of cycles. So thank you for your attention, and I'll see you next class. Goodbye.